Thanks for that. The session is now being recorded, so good morning if you're just watching the YouTube. Yeah, the Zoom link was on an announcement that I put on the Quarkus webpage, and also if you can find the MWF lecture schedule, which is one of the links towards the top of your Quarkus page. There's a page with all the lectures and all the video recordings there, and it has a link at the top there as well. So I'm going to share the screen. What's the weather like in Toronto right now? Well, I rode through it. It was pretty nice, a little cool. I had to wear a bit of a jacket, but it was okay. I'm going to share screen too. So this is what we're working on today. We're into class 2. I want to talk about a little bit about modeling and making a rough estimate from chapter 1 of the Etkina. I'm going to talk about physical quantities and significant digits. Then we get into chapter 2 stuff. So what is motion? How do we keep track of motion using motion diagrams? And there are a couple of nice videos that I put on your Mastering Physics that you can look at between now and the end of chapter 2, the next couple of weeks. And one of them, this is from one of the videos where they show a turtle going along and making a motion diagram of the turtle's motion. But actually, before we get going on that, the next slide is that I think there may be a PhysU representative here. So I'm going to click on Stop Share and see if anyone here has raised hands. So actually, if you are the PhysU representative today, can you raise your hand, and then I'm going to unmute you for a second because there's a presentation here. Or type it into the chat window who you are. I don't see you here. Can you announce to me who you are? Is it Rosalie? Are you the PhysU person? Actually, what I'm going to do then, Rosalie, is I'm going to promote you to panelist. You're going to have to rejoin. And so now you should be able to talk.
Okay, hi. Is my audio working?
Yes, I can hear you fine.
Okay, perfect. So I'm going to share my screen here.
Great.
Oh, it won't let me.
Oh, sorry. I have to change my share screen preferences. Hold on a second here.
No worries.
All panelists. Rosalie, can you try again?
I hope everyone can see this.
I think it's good.
Okay. So, hello everybody. My name's Rose and I'm here on behalf of the Physics Student Union. I'm the president. Oops, sorry, this is the wrong slide. So if you haven't heard of us, we're the Undergraduate Physics Student Union. We represent you guys in conversations with the department, and we ensure that your concerns are brought to the attention of the appropriate people. We also host various social and academic events, including study sessions throughout the school year. In normal years, we also have a lounge in McLennan Physical Laboratories where you can visit us and meet other students. Unfortunately, the lounge is currently closed until further notice, but if we open up during the school year, you're welcome to come check us out. If you'd like to get involved with us, please consider running for the position of first-year representative to be elected in early October. If you're not running, be sure to at least come and participate in the election, which will be held online. Additionally, please show up to our events. It's an amazing way to learn more about physics and the department and to get connected with other students in various fields. Also, engage with us on Discord. We have a giant server that serves as our virtual lounge, and you can meet your fellow students and ask questions there. If you're interested in becoming more involved, please consider running for an executive position at the end of the school year when we elect our new team. So once again, you can find us on Discord. The link is on the screen. This is for discussion with other students. It includes group chats for every physics and math course, as well as some astronomy courses. If you've never used Discord, we have a video tutorial available for you. You can also find us on Facebook. We have a page and a group. The group is linked here. And for private concerns, feel free to email us. We've sent all this contact information to Professor Harlow so that he can share it with you guys on Quarkus or Piazza to access after class. That's it from me. On behalf of PhysU, welcome to the department and good luck with the fall semester.
Wonderful. Thank you, Rose. And yes, I did put that message. I posted it on the Piazza page. So hopefully everyone can find that on their corpus.
Okay. Perfect. Thank you.
Okay.
Have a good lecture.
Thanks a lot. I'm going to go back to sharing my screen. Okay. So let's see. Just let me move my windows around so I can see the question and answer. And I also want to be able to see the chat here. I've turned the chat onto just so that I think so that only I can see it. There it is. Yeah, I can probably post those links. They're in the like I say, they're on the Piazza, so I think that's the easiest way to do it. And we can also look at panelists, participants. Okay, I'm not seeing any raised hands at this moment. Okay. So there was, I've been noticing on the Piazza, there's a lot of questions about the week 1 pre-practical assignment. You should see this on Quirkus right now. There is a different due date depending on which practical section you're currently signed up for, but it's somewhere between September 20th is the earliest deadline, or it might be as late as September 23rd, depending on you. Someone asked if there's a time limit. So it does record your time, but there's no time limit. You can take as long as you want on it. We are hoping it doesn't take you more than about 30 minutes. So hopefully that helps with that. I think that's all my pre-announcement stuff. And I'm going to get into some physics stuff. Someone asked if they, if you requested a change to your practical time, when should I expect to receive an update? So hopefully that should be before your first practical. April's got a lot of these to deal with, and so you know, she's doing them in order as quickly as she can. The videos of the turtle had a deadline. Ooh. Yeah, I didn't mean there be a deadline of September 11th, so I could change that. That's a good idea. Take a look. And I don't know how the pre-practical assignment is being marked, but if it's not auto-marked, then it will be updated when your TA looks at that. Okay. Great, great, great. So what is physics? So physics is a course, obviously, that you take sometimes, but here in this department, when we say physics, what is physics? Physics is something that you do. What are you doing this evening? Well, I'm doing physics, which means I'm going down to my lab and trying to fix the leaks in my cryostat or something. Or maybe I'm reading this book, or I'm working out a big physics, problem where I'm trying to design my, a new experiment. So here are some things that physicists do with our time: collecting and analyzing experimental data, making explanations and then testing them, creating different representations like pictures or graphs or bar charts or equations or something that represent physical processes, finding mathematical relations and models between different variables, and then you can test those in experiments. That's what I sort of mean by doing physics. And one of the things that we do to simplify real objects in this course especially is make these point-like objects. So I told this joke about the modeling a cow as being a point-like object. So here we have sort of a real-life photo of a race car. So that's what's going on and represents a lot of complexity. You can see the wheels that are turning, and you can see the guy in there driving it, and there's rear view mirrors, and there's a lot of things going on. But what really matters is how fast the whole car is going and where the car is. And so what you can do is you can just draw a point, and you can say, so this is the model. You can just point at it and say race car. Whoop, race car, you just draw a dot. I don't care. Okay. And that's your model. So let's do a quick little poll. What is the approximate density of water? So I'm asking you to make an estimate here, and don't go and just look up. Is it 10 to the minus 5 kilograms per meter cubed, 0.01, 0.1, 1, or 1,000? And these are all in units of a kilogram per meter cubed. So think about it, what a kilogram is and what a meter cubed is. Tell me your answer. It's covering up again. A is 10 to the minus 5 kilograms per meter cubed, B is 0.01, C is 0.1, D is 1, and E is 1,000 kilograms per meter cubed. Give you another 5 seconds. Okay, thank you. A lot of you voted in there, and it's pretty interesting actually. I'm gonna end the polling and share the results with you. So there's a smattering of results all around these different numbers, as sort of a guess, but about half of you, about 33% of you said D, that's 1 kilogram per meter cubed, and 36% of you said E, 1,000 kilograms per meter cubed. So these are off by a factor of 1,000, but one of them's right and one of them's wrong. So let me show you what I think. I mean, you can't look it up, but I think if you think about what a meter cubed is, what a meter cubed is that's a meter high, a meter wide, and a meter deep. So if you think of a bathtub filled with that much water, the question is, D, would that weigh 1 kilogram, or E, would that weigh 1,000 kilograms, and which kind of seems a little closer to you? And I think that just, you know, with sort of my own common sense, I can think that that much water that you could actually get into has got to weigh way more than a kilogram. 1,000 kilograms maybe seems like a lot, but I guess water is pretty heavy. And if you just have a choice on multiple choice between 1 or 1,000, I would say it's got to be 1,000. So this was sort of an estimation kind of problem. And there, the next slide is density. Density is the amount of mass per unit volume of a material. So mass divided by volume. So the unit of density is either kilograms per meter cubed or grams per centimeter cubed. That might have been what you're thinking about actually, is that the density of water is 1 gram per cc. So 1 is the number if you're measuring those units. But then when you convert it to kilograms per meter cubed, it actually goes up to 1,000. Let me take a quick look at if there's anybody on the with hands raised. If there's any questions. Again, I'm not seeing anybody with their hand up. Hopefully that's working. Someone asked for this lecture under the required readings, it said practical 1 material. What does that mean? So this means that, it just means the way of keeping track for me is that the stuff that's in this lecture is stuff that you're supposed to have covered before you go into your week 1 practical, which is next week, because here we are. It's a good question. And what is the symbol you use for density? That's also a good question. So I usually use the Greek letter rho. It looks like a little bit like a P, but it's called rho, as in row your boat gently down the stream. Okay. Okay. Oh, there was a hand, but it went away. Let's continue along. This is a little bit about physical quantities. There's this is part of your reading. The SI unit system, it stands for System International. It is a system of units, which means what standards that we can measure everything in. And so the SI unit, for example, for measuring length is the meter. And this has a definition, which is a meter is the length of the path traveled by light in 1 divided by 299,792,458 of a second. So a very small fraction of a second. That's how far light travels. And then there's actually an SI unit for time. The SI unit of time is the second, and the second is defined by actually a particular emission line of a cesium atom, which sends out a wave which has a period, which if you count up 9 billion exactly, 192 million, etc., of these periods of that cesium emission, that will be 1 second. That's your definition. And then also tied up with these, and it's a bit complicated because there's also this thing called Planck's constant. We have a definition for mass. Mass is for the kilogram. The SI unit for mass is the kilogram, and the kilogram is defined by length and time and this special number called Planck's constant. So it's a little, you have to go on a Wikipedia page to really kind of get through the details, but that's not part of this course. The main thing is that meters, seconds, and kilograms is the SI units we'll be trying to use in a lot of our calculations in this course. And then there are prefixes which you can put before these basic units to represent big numbers. So tera is 10 to the 12, giga is 10 to the 9, mega is 10 to the 6, kilo is 10 to the 3. Sort of interesting that kilogram is already an SI unit, and a gram is a thousandth of that. So I guess a millikilogram is a gram. So then that's greater than 1, less than 1 is deci, centi, milli, micro, which is represented by this Greek letter mu, which is like the sound that cow makes. And then nano is n 10 to the minus 9. So these are good things to just kind of be familiar with. Okay, so next on the list is significant digits. I want to talk a little bit about that. Let me look at the question list here. Things are coming up. People are typing Q&A. Why cesium? I think cesium is just easy to, it has a nice emission line that's easy for people to measure, and it's very arbitrary. Someone just chose it. I mean, the second, and everything was chosen to kind of match historical definitions of the second. And so there were previous definitions of the second as being 1/86,400th of a day, and it was based on the Earth's rotation. That doesn't work well because the Earth doesn't rotate all that well. Originally, I think the definition of the second was every time Galileo Galilei's heart beat. So he used his pulse to measure off seconds back in the year 1600. And so I would say that wasn't very good because his pulse rate changes. Okay. So significant digits is the number of significant digits is the number of reliably known digits in a number. And it's usually possible to tell the number of significant digits by the way a number is written. Example, 23.21 centimeters. So if someone told you the length of something was 23.21 centimeters, then you just count the digits. 1, 2, 3, 4. This is 4 significant digits. Then 0.062 centimeters. You might think that this also has 4 significant digits, but the idea is that those initial zeros don't really count as giving you some reliably known digits of the number. What they are is placeholders to make you know that that 6 and the 2 are talking about the 100th column and the 1000th column. And one way I kind of like to remember this is sometimes I write it 6.2 times 10 to the minus 2 scientific notation. And then you always get the right number of significant digits. And then 80. Someone says 80 kilometers. That could be either 1 or 2. I'm not quite sure. You know, it's a little, I guess you could say it's ambiguous. 1 if just the 8 is significant and it may have been rounded. So about 81 kilometers, but we just say 80. And if it's exactly 80, then that would be 2 significant digits. And then if you put 80.0, then all of a sudden you know that this 0 must be significant because you put a 0.0 over here. So all of a sudden this has 3 significant digits. So that's interesting. Rules. So when you are multiplying or dividing numbers, the result, the factor or the quotient, I guess, has as many significant digits as the number in the calculation that had the fewest significant digits. Example, 11.3 times 6.8. So maybe I'm calculating the area, for example, of a rectangle that is 11.3 centimeters wide and 6.8 centimeters in length or something, or width and length. If you times those on your calculator, you'll get 76.84. However, 6.8 had only 2 significant digits. So it's sort of best to round your final answer to have the same number of significant digits as the least precise number in your calculation. Otherwise, if you put 76.84 centimeters squared, that's a typo right there. Centimeters squared is the units of area, not centimeters. So that should be the squared as well there. And again, I'm not sure if people are got their hands up. Robin, would you like to ask a question while we're on this?
I put the questions in the Q&A for you. I don't know if you can see them.
Sure. There it is. I was taught that 80 could be read as 1 or 2 significant digits, but that 80 was always 2. Does apply for this course? Yeah, I don't know. I mean, I'm not quite sure what you're asking there, but I mean, there's no real standard, right? It's just if someone writes 80, I think you have to know what context they had written that in. If it was a precise number of kilometers, 80, or if they were just casually saying around 80 when actually it might have been 78 or 82 or something like that, but they say 82.
My question is, let's say as a final step in a question, we had 16 times 5.0, right?
Right.
So we'd have 80. How would I express that answer? Do I write
that's
8.0 times 10 to the 2 or?
Yeah, both times 10 to the 1, actually, yeah. So it's really terrible, isn't it? But yeah, I think if you write, that's a great question. So let's say your answer was 80 and you knew it was supposed to be 2 significant digits. If you write it as 80, then the marker might say, well, you didn't do the right number of, maybe that might be 1 or something. And so if you want to be extra careful, you could write 8.0 times 10 to the 1, and then that would be 80, and you'd specify it that way. But I don't think any of your markers are going to be that picky, actually. Okay. So that's a great question. And William, do you have a question? That's at the top of my list.
Yeah, can you hear me?
I can.
Yeah, yeah, cool. So on that picky marker part,
yeah.
if we get like, if we don't follow the sig fig rules, let's say I wrote like 76.84 on one of my answers, but I get a mark off.
Oh, like do you lose points for significant digits?
Yeah.
Or something? Well, it's something you could always ask. Maybe it's, I can't imagine myself doing that. It would, it's something that you can ask your TA, I guess, depending on the assignment.
Okay.
I think a lot of these quizzes, as we get closer to the quiz, I could tell you the answer to that, maybe. I think it's good to know, right?
Okay.
But yeah, I don't know the answer to that question. All right, I'm gonna. Okay, I think I'm gonna continue on this. It's good to know these rules, even if you don't lose points for them. Sometimes the number of significant digits by these rules might be off. It's supposed to be kind of an estimate. Scientific notation, I've already talked about that a little bit. It allows the number of significant digits to be clearly shown no matter what. For example, if you don't know how many significant digits are in 36,900, you can always write it as 3.69 times 10 to the 4. And then we know absolutely clearly that there are 3 significant digits because you've got, these are the significant digits, and the times 10 to the 4 gives you that place. But if you were to write 3.690 times 10 to the 4, then that's the exact same number, but you kind of think it's more precise, 10 times more precise, because you've got that extra 0 there. So let's look at these numbers. There's 82. I think these should all be unambiguous. 0.0052 is B. 0.430 is C. And 4.321 times 10 to the minus 10 is D. So we're asking you to rank from the most to the least the number of significant digits in the following numbers. So I'm going to start the polling, which hopefully doesn't cover this up for you. Poll. Relaunch poll. I can see what you think. Okay, 75% of you have voted. Another 10 seconds. Okay, so I'm going to end this polling and share the results. So 88% of you voted for C. So let me just see what I think about that. So 82, I think, has 2 significant figures. 0.0052, that has 2 significant digits because all those zeros are placeholders. This one's weird because this first 0 is a placeholder. It sort of has to be there. But this last 0, you didn't have to write it. 0.43 and 0.430 are the same. So if you added an extra 0, you didn't have to. The only reason you would have done that is if it was significant. So this is now 3. Does that make sense? You don't have a choice for that first 0, but you did have a choice for the last 0. And since you had a choice, and you chose to write it down, you must have measured it, I guess. And this one just has 4. So right, so it's going to be D is greater than C, and then is greater than A and B, which are equal. So I like that a lot. Excellent. This is my daughter. This is actually from a couple of years ago, but at the playground. So this is before COVID times and having fun at the playground. And she said, "I don't like the significant digits on that conversion, Daddy." So we're going to talk a little bit about converting. What it says on the sign on the playground is no smoking within 9 meters or 29.5 feet of playground. Okay, so I agree. There's something wrong, I think, with having all these significant digits. And so the question is, which is it? Should this have 1 significant digit or 3 significant digits? And so I actually went to the bylaw from www.toronto.ca, and there's legal documents about smoking. So in 2013, City Council voted that while in a park, no person shall smoke within the boundaries and a 9-meter radius surrounding the playground. So clearly, City Council only really intended 1 significant digit in this rule. So if you're going to work this out, you can do these conversions. One of the ways I personally like to do a conversion is to multiply by 1, where 1 is something that you know. So a fact you might know is that 1 inch is 2.54 centimeters. So 1 inch divided by 2.5 centimeters is 1. You can flip that if you want. Also, there's 100 centimeters in a meter, and there's 12 inches in 1 foot. So if we have a number, like a distance, which equals 9 meters, and we would like to convert that to foots, then we can use this. Actually, I don't have inches. I want to use foot to inches. I have centimeters here. So actually the first thing I'm going to have to do is do a conversion from meters to centimeters. So I put cm up on the top and meters on the bottom. And then, and it is, when you do that, there's 1 meter is 100 centimeters. And then I'm going to times it. So now centimeters, I'm going to times it by something to get rid of the centimeters and convert it to inches. So I'm going to put inches on the top and centimeters on the bottom. And that is going to be 1 inch is 2.54 centimeters. And then I'm going to times it by, now I've got it to inches. I know that there are 1 foot is the same as 12 inches. So and just to kind of check, my units are canceling there, whoops, kind of nicely, is meters cancels meters, centimeters cancels centimeters, and inches cancels inches. So my final answer should be in foots. And so 9, it's going to be 9 times 100 divided by 2.54 times 12 in bracket. And when I did that on my calculator, I got 29.523 foots. And so then we do our rounding. Last step is that since there was 1 sig fig in the original thing, then you should just do 1 sig fig. So I'd say D equals 30 foots. But then, as Robin pointed out, that's, who knows, is it 1 significant figure or 2? So I guess if you want it to be really ridiculous, you could say 3 times 10 to the 1 foots. And that's even just worse. I would say 30 would be what I would say. But 29.5 is wrong. Okay. Just quickly going along. We're getting a little bit behind time here. So let me, because I want to get into chapter 2 today. Ooh, some people are saying they couldn't see the polls. Well, the plural of foot is feet, not foots. Thank you, that's right. All right, so this is the suggested problem-solving strategy. This is, we're kind of finishing up chapter 1 here, which we'll talk a lot more about in practicals, but this is sort of a 4-step process that you can use for solving any physics problem. And the first step is sketch and translate, which means you draw a sketch of the situation and write down kind of your knowns and unknowns. You're trying to translate words into kind of math, like numbers and stuff. Simplify and diagram is you kind of neglect some of the details which might be irrelevant and choose some sort of representation, which means try to find sort of which chapter you're in and what kind of problem it is. So how you're going to represent these variables and what equations might be important. Represent mathematically is that you write down those equations and try to solve for your knowns symbolically or unknowns symbolically. And then solve and evaluate. Your last step is to plug in your numbers, come up with a number, and then look at it to see if it makes sense. Like, does it make sense that there's 1 kilogram is a cubic meter of water? You can kind of think that kind of thing, a sanity check. We're going to be doing lots of examples of this 4-step process in using in working through problems, not just here, but also in your practicals. So, but I wanted to get it out there so you know what it is. And Abdullah, you have your hand raised. Can I unmute you for a second? See what. Do you have a question? Sometimes if you don't want your hand up, you have to unraise your hand. Going once, going twice. Okay. Okay. Actually, Annie, I just see that your hand is up, so let's try you. Annie, do you have a question?
Hi, can you hear me?
Yes, I can.
I was just wondering, for that, I was just thinking back to the 80 question for the sig figs, and I remember that in grade 11, my teacher told me a trick that you could put a period at the end, and that would significant the 2 sig figs.
Yeah, I've heard that too. My problem that I have with that is that, first of all, periods are kind of small, and maybe people might think it's just like a dot or, you know what I mean, like a little random dot that didn't mean to be there. That's problem number one. And also the other problem I have with it is that a period is a thing of punctuation, right? So maybe people might just think it's the end of a sentence, and it's kind of weird to write it in the middle of a sentence. But yeah, you could try that. I don't think anyone's going to pay attention to the period, though. That's my problem. In real life, it's kind of a silly way to do it, I think.
Okay.
Not
thank
silly,
you.
but I just think it's probably, it's certainly not something I've seen a lot of people doing in real physics. They just write everything in scientific notation, actually, even
All
if
right.
it looks annoying. Okay.
Okay, thank you.
Yeah, sure. Thanks for that, though. Okay, she's back on mute. Okay, so I think we're getting into chapter 2 for the next time is 11:46. So let's just go through a little bit of motion. I have a quick little demonstration I'll show you. First is this idea that motion is kind of relative. So we have here an observer on Earth sees the sun moving across the sky. The sun rises in the east and then it goes overhead and sets in the west. However, an observer out in space, deep space, would see that the sun is just sitting there, and they would actually see that you as a person are standing on a rotating Earth, and so you're moving this way from west to east, so that the sun appears to be moving over your head from east to west. So an observer describes the motion of the sun differently than an observer standing on the Earth. And who is right? It depends on what the object of interest is and what the observer is. And you have to describe, specify who the observer is when you're describing motion. So what is motion? Motion is the change in an object's position relative to a given observer during a certain change in time. If you don't identify the observer, it's impossible to say whether the object of interest moves. Physicists say that motion is relative, meaning that the motion of any object of interest depends on the point of view of the observer. And this was first brought up and kind of really made famous, I guess, by Einstein's theory of relativity published in 1905. And there was an old joke, which is, so Einstein is on a train and he flags down the conductor, says, "Conductor, when does New York arrive at this train?" So specifying the observer is important before describing the motion of the object of interest. A reference frame includes some object of reference and a coordinate system, like an XY axis or something. And that can be moving or it can be, it's usually stationary relative to some object. Like, for example, this lab room I'm in is a stationary thing, so I can draw an X and Y axis and say that's my reference frame. And then you need a clock to measure the time. And that's part of your reference frame. So some simplifying assumptions are made in order to analyze complicated situations. And in chapter 2, we're doing a lot of linear motion. So linear motion is a model of motion that assumes, first of all, that the object is moving as point-like, and that it's moving along a straight line. So it's not turning. And that's sometimes pretty close to the case. So Etkina uses a lot of motion diagrams, and this is what my demonstration is about. It's a way to study motion. One way to study motion is just make a video, right? And so videos have different frames. When you make a video, you might have some number of frames per second. Sometimes it's 30 photos of the same situation per second. And each separate photo is called a frame. And so here's a car that's driving along and a tree which is not moving. And in every frame, the tree is at the same position because it's not moving. But the car, since it's moving, shows at a different position in each subsequent frame. So as time moves forward, the car changes its position. And so you can make a motion diagram by taking all those frames and stacking them on top of each other. This would be a composite photo, kind of all the different frames. And the same amount of time elapses between each of these cars. So there's not 4 cars. There's just one car in this motion diagram. And to make it a little less kind of complicated, easier to draw, we go a little further. And in Etkina, we say a motion diagram is a bunch of dots. And each dot represents the position of the center of this car at a different instant of time. And all the instants of time are separated by the same interval. So I can try to kind of do that. I'm going to stop my share here. Put this here. So you should be able to see me now a little better. I'm going to take my video and aim it over here at a little demonstration that I have set up for you. So here I am in my lab room. What I have is I have a bunch of bean bags, which I can throw around. These are going to be used for the dots. I have a rolling cart, which can either go really fast or it can go really slow. And I have a penguin. And the penguin is actually a metronome. And what the metronome does is every time it ticks, it's telling you when to put a dot in the motion diagram. And every tick is happening at an equally spaced amount of time. Sounds like a little bit less than a second to me. So grab a bunch of these bean bags. This is what Etkina does. And then I'm going to try to, every time I hear a tick on the metronome, I'm going to throw a bean bag down. So we're going to start with a sort of a fast motion here. Today one of these fell off. So these 1, 2, 3, 4 dots or bean bags represent the position that this cart was in at those 4 ticks of that metronome. That was one motion diagram. Now, if I take the cart and move it a little slower and do ticks, what do you think will happen? What will happen to the spacing of these dots? Okay, let's do it a little slower. Those look about the same. It's nice and slow. That is slowing down actually. So you can see now that these dots are pretty closely spaced. Okay, so they're equally spaced in time, but since the object was moving slower, the dots are closer together. I do have a little poll for that. Make sure we're paying attention. Yeah, I think I skipped the scaling things that were in the pre-class notes. Sorry about that, because it's not in the textbook. So hopefully you can see these 2 objects, object A and object B, 2 motion diagrams. My question is, which one is going faster, A or B? You can see this poll. Maybe another 5 seconds. I'm seeing anonymous people saying, why can't I see the poll? So you'll have to unanonymous yourself and we have to deal with that. I think about 90% of the class has voted. And the end polling. So the results are 6% voted for A and 94% voted for B. And yeah, I'd like to answer B. So since it's the same amount of time between dots, the distance traveled between the dots was farther for that same amount of time, so it's going faster, okay? Whereas opposed to, it must be slow to leave behind so many dots, or so many, I guess, bean bags as you're going along. So good. It's a little bit about vectors coming from chapter 2. If you have 2 vectors, A and B, and you want to add them, one way of doing it, there's a few different ways you may have learned back in math class. But one way is called the tip to tail method. So you draw A, you place the tail of B, this is like called the tail. And this is, oops, T. Such surprisingly bad handwriting. Tail. And this is called the tip. And place the tail of B at the tip of A, and then you draw a new vector from the tail of A to the tip of B. And that new vector is called the vector sum. It's A plus B. If you wanted to subtract, then the way you do that, A minus B, is you basically do A, so A minus B is equal to A plus negative B, where negative B is a vector which is the same length as B but in the opposite direction. So you just flip the tail and tip of B, and that's negative B, and then just add those. And again, you draw a new vector from the tail of the first vector to the tip of the second one you're adding, and that gives you A minus B. It's a good little review. And you can draw motion diagrams with vectors as well. You put average velocity vectors would be like a green arrow or arrow between each dot and the next subsequent dot in the motion diagram. And so it's the tortoise versus the hare. Hare means rabbit and tortoise means turtle. So the rabbit goes faster than the tortoise. So the velocity vectors are longer. A longer velocity vector means it's a faster motion. That's another way of looking at that. And then position time graph. So what I want to do is imagine that I've got a ball and I take it and I start it down here somewhere at 0 centimeters. And then I move it upwards very slowly, taking 10 seconds to move it up to the 20 centimeter mark. How can I, what's a simple way to describe that motion? Well, I could do a motion diagram and get a lot of little dots. But there's another way called a position time graph. And these are going to be really important going forward, so let's quickly introduce them. One way of keeping track of the position of the ball in between 0 and 10 seconds is maybe you could make a table. Every second you list the position. So it starts at 0, at 1 second on the stopwatch, at 2 centimeters, at 2 seconds on the stopwatch, it's at 4 centimeters, etc. And you get these pairs of numbers. So for each second of time or some unit of time, you list the position of the ball. And once you have a table of pairs of numbers, you can make a graph or a chart of the motion. You can put the left-right location on the graph to be the time, and the up-down position on the graph to be the position of the object. So what you'd get is as it's moving up, you make all these dots, and in this case, if it's going at a steady speed, you get a bunch of dots in a straight line. And what you can do then is you can connect the dots, and Etkina calls this the trend line. And this seems like a pretty simple thing to do, but it's actually quite deep. What it means is that somehow, when we've drawn this line, we feel that we know like the instantaneous position of that object at any instant of time. Even though we only measured it at 10 different times where the dots are, we feel that to get from here to here, it had to smoothly go through kind of like an infinite number of tiny little positions from here to here, and that in those infinite little time moments or something, that we know where it was at all those times. So it's called a position time graph. And let's do another poll. So Mia knows how to ride a bike. And even if Mia doesn't know, if you can imagine knowing how to ride a bike, then you can make it happen. It just takes time. Anyway, she's cycling along a straight stretch of track, so it's 1D motion. Her speed is 12 meters per second. So which of these position versus time graphs, only one of them is just not possible for this description of Mia's motion? I'm hoping you can see the poll and see the graphs and choose which one. Oops, stop, wrong. Okay, so now you can answer, I think. I'm running out of time here. So we're going to have to run because I've just noticed that it is 12 o'clock. And I know that some of you have another Zoom class to be at, but if you can give me another minute, we'll finish this up. So a lot of people are saying that D was impossible. And exactly right. So here, if X versus T is it's a horizontal line, that means that the thing is not moving. So I'm going to keep that ink. I'm going to go along a little bit. Let me just quickly show this almost at the last slide here. Imagine you steadily walked 7 meters away from your house, and then it took you 5 seconds to do that. Then you stopped for 2 seconds and checked your bag, and you ran back to your house in 3 seconds. You can make a plot of position versus time for that motion. Here's walking. It took you 5 seconds to walk that 7 meters. Here's checking your bag. You're standing perfectly still, and you've got a sort of straight line. And then you turn around, and you're running back. And you can see the slope here for running is greater than the slope for walking. And so that's one way of checking the speed of something on a position time graph, is by looking at how steep the curve is. If it's a zero slope, it means you're stationary. And if it's a steep slope, going fast, and a shallow slope, going slower. So I'd like you to read about the vector math and position, displacement, and distance. There's already been some good questions on Piazza about that, which I'll address on Wednesday. And something to think about between now and then is, does constant velocity imply constant acceleration? And the other question is, does constant acceleration imply constant velocity? Thanks for your patience. It's now 12:02. I'm gonna have to end this, but I will go over to my gather town next and see if there's anybody who wants to gather around at the office hours, and we'll see how that works. So thanks very much. See you Wednesday.